Hi, my name is Janet Page. First, just a few things about me. I'm currently a postdoc at the University of Michigan, and I work with Karen Smith. Before this, I did a one-year postdoc at the University of Bristol, where I worked with Fatemeh Mohammadi, and I got my PhD in 2018, and my advisor was Kevin Tucker. So my hope for this video is just to give you a general overview of the type of questions I like to work on. So I work in commutative algebra and algebraic geometry, and I really enjoy problems which can be solved using combinatorial methods. So to me, this can mean two different things. It can either mean that I start out with some ring or ideal that has some rich combinatorial structure, or that in whatever problem I'm trying to solve, I try to distill the problem into any combinatorial data that's relevant and associate the right combinatorial object to try to make the problem easier to solve. So for example, some of my favorite objects to start with are toric rings, which are rings that can be associated to a cone and a lattice or a polytope. And of course, the combinatorics of the cone or the polytope can tell you about the ring itself. Another class of rings that I work on ever since my dissertation is Hebe rings. So Hebe rings are a class of toric rings, actually. So they're affine semigroup rings, but they can be associated to a finite poset. So they actually have stronger algebraic and combinatorial data than a more general toric ring. And a lot of the data of the Hebe ring can actually be read off immediately from the poset. So you can look at the poset and tell things like dimension or whether or not your ring is Gorenstein just by the combinatorics of the poset. Another class of combinatorial objects I work with, not so much in my own work, but in running RUs, both 2 summers ago with another postdoc or this past summer with 2 other postdocs, are square-free or more generally just any monomial ideals. So of course, square-free monomial ideals can be associated to a simplicial complex in a few different ways. So here's one of them. And the combinatorics of the simplicial complex can tell you about the ideal itself. Okay, so what types of questions do I like to ask? So most of my work falls under the category of singularities and positive characteristic. And the project I'm going to be telling you about, I'm going to give you a little preview for my talk on Monday, is going to fall into this category of singularities and characteristic P. More generally, I like studying just any properties of rings of ideals. So for example, recently I've been really interested in studying the non-Gorenstein locus of certain combinatorial rings. So we study this using something called trace ideals, specifically the trace of the canonical module, can tell you how far your ring is away from being Gorenstein. I've done a little bit of work on things like symbolic and ordinary powers of ideals. This was also related to the RIU I ran a couple summers ago, and more recently I've been thinking a little bit about rings of differential operators as well. So I'm going to give you a little bit more of an advertisement for the talk that I'm going to give on Monday. So we're thinking about something called extremal singularities and positive characteristic. This is joint work with all of the authors listed. The first group, we have 2 different papers out. One is called Cubic Surfaces and Characteristic 2, and it's in Transactions, and the other is called Extremal Singularities and Positive Characteristic, and it's still in the archive. And the second group of people, this is ongoing work, so we don't actually have anything out yet, but hopefully this semester we might have something on the archive. All right, so this project actually started out in Banff. I joined the project afterwards, but the original question was one posed by Karen Smith, and she was thinking about cubic surfaces in characteristic 2 and trying to see whether or not we could understand all the non-F pure ones. But it turned out that these kind of generalized to a really special class of hypersurfaces. So I'm going to motivate the question a little bit differently. So we could ask, what is the most singular possible hypersurface of degree D in positive characteristic? And one answer to this is those with minimal F pure threshold. So we actually answer this question precisely by giving a lower bound on the F pure thresholds. The F pure threshold is something which measures singularities and positive characteristic, and the smaller it is in general, the more singular your variety is. So we find exactly those hypersurfaces of degree D, which achieve this lower bound, which is in terms of the degree on F pure threshold. And it turns out they have a lot of really fascinating algebraic and geometric properties. They have a matrix factorization that sort of mirrors the theory of quadratic forms. So that's where the algebraic data comes in. And yeah, they've got some fascinating geometry. So the ongoing work I'm doing is focusing specifically on the surface case and looking at the linear spaces on these things. And they've got a lot of really special geometric properties as well. So we also classify these things precisely. So it turns out there's only finitely many of them, of these extremal hypersurfaces, up to linear change of coordinates and any degree and dimension. And we're able to tell you exactly how many there are. Actually, this is an example of a problem that we were thinking about for a long time and kind of thinking about it the wrong way. But it turned out if we just associated a directed graph to these, then we were able to to classify them precisely. So this was an example, this classification of them was an example where we really just had to distill the problem into the relevant combinatorial data and associate some combinatorial object, and it made the problem much easier to solve. All right, thank you so much. I hope to see you all on Monday.